All right. Okay. Thanks, guys. So let's get started. So first of all, I wanted to see. Well, I mean, before everything, so I did the homework just to share your suffering, not just to dish it out, but to take it a little bit too. And it was a lot of work, but it was good. Um, but I think it is a lot of work. I don't know how many of you guys have done the homework, but again, I want to emphasize if I, and I'm just going to really quick after we get done with some of this housekeeping, just talk about the concepts we've covered. The concepts are, I feel, are really simple that we've covered so far. We've got like a couple of models of this diode of current versus voltage. Not a whole lot of circuit sort of base. We've sort of looked at the voltage regulator a lot and different levels of completion. But so the main thing about this class is being able to analyze circuits, to see different diode circuits so far. The next few weeks you'll be seeing transistor circuits, and to be able to analyze them. So as far as I'm concerned, this class is all about doing the homeworks and getting practice. And sort of circuit design is like that. You gotta like do it, and then you kind of get a feel for what the circuit's gonna do, and then you'll have also level of math and the level of approach. I shouldn't say math, because a lot of times you gotta just even think about what type of approximation you use and all that stuff. So anyway, so long story short, I feel it's really important for you guys to do the homeworks, to do well in the class, or to understand the material. So, and I figured I'd give you guys like the long weekend to finish it if you haven't done it, or if you need to catch up. So the quiz is going to be on October 13th, which is a week from today. So next Tuesday. So that's one. Two is I kind of put in the lecture kind of late. I forgot when I uploaded it. Maybe it was even last night or yesterday. So I just wanted to see if anybody had a chance to look at it. And you're welcome, Amber. So just to look at it, and do you have any questions about it? Sort of in a nutshell, I covered the full wave rectifier circuit, and it's really, sort of at first I talked about with the half wave rectifier. We'd already talked about what issues it had with this unwanted ripple, and how we could basically try to improve the performance by looking at both halves of the input cycle, and dumping charge sort of twice as fast onto the, sorry about the handwriting here, it's pretty awful, but sort of getting to this equation here where for the full wave rectifier, that basically gives you half as much ripple for all the same component values, the same load resistance, same smoothing capacitance, same input frequency, at a very small sort of degenerate, it's a small cost of, there's a 2 VD on here, whereas in the half wave rectifier was 1 VD on. And this is for the ripple voltage. So we're effectively cutting the ripple voltage in half by using like 4 diodes instead of 1. And then I talked a little bit about how 4 diodes, it wasn't a huge amount of deal, because 4 diodes, it's not like really a significantly higher cost or higher area than 1 diode, just because the way semiconductors are. So anyway, just any questions about that, and you're also welcome to email me or anything else. So everybody good with that? Okay, so if not, and if feel free to jump in later too. So the rest of the class, I was really going to go over the sort of some of these homework problems, and because again, they're very, very important. So let me just say one thing. I feel like, sorry, I was thinking about this. So when I was in undergrad, God knows I didn't do enough problems, and I was all about reading the book. Where am I? So I feel like we've only, the only conceptual things we've covered in this class is some very simple stuff. We talked about, we've got this thing called a diode so far. We have a diode. It's got a couple of models. It's got this. It's got this kind of exponential of VD over T. So we got this kind of equation for this, and then we've got this one, simplifying model of either, VD, ID. So one of these, either, this was ideal, and this was constant voltage. And then we had this approximation of if you take something out here and you really zoom in, if you zoom into just a section of that, so this is a zoomed on part of a VD-ID curve, that if you're talking about very small values, then you can approximate that as a line, sort of this exponential thing. And this ended up being called the small signal analysis. So just for that very small part of the current versus voltage curve, you could pretend like the diode is a resistor and use simplifying assumptions. Okay, so this is, as I was trying to think of what we really covered the last 6 weeks, this is it. I mean, from a conceptual standpoint. I mean, you could say, well, there's lots of details, and I've been lecturing, so I know, we've spent many hours talking about the specifics of the details. But in a nutshell, that's pretty much it. Everything else is doing, how this simple diode thing, this piece of microelectronics, can be used in different configurations with other diodes or resistors or capacitors and so on to do different circuit functions. Okay, and that the only way you guys are gonna, be able to understand that is by doing the problems. So anyway, that was just a long way of saying do the problems. Okay, so so I think for the rest of the lecture, I was going to go over some of these homework issues. And I wanted, before I do that, I was wondering, is there a particular problem in the homework anybody has questions about? Otherwise, I would just kind of go from top to bottom and try to give some hints about how to do different, how to solve these things. So any questions? Any requests?
Oh, I think I'm good. Thank you.
Okay, thanks, Juan. Anybody else? No? Okay, well, so let me go through these then. So where we started, I don't know, God, it must have been, I don't know, 20 problems or something like that, but it started with some kind of warm-up exercises. Obviously, it's simpler to start with the ideal diode. And so it's asking, when he says, looking at problem 3.9, it's asking to plot input versus output. So that means V out. So I was telling you guys that there are 3 types of graphs in this class. One of them is voltage versus current. The other one is V in versus V out. And the third one is time versus voltage. And so those are ways that we can kind of visualize circuit performance. So when it says input, output, it's basically saying, I want you to give me this graph, V in versus V out. And then it's saying assume an ideal diode, and ideal diodes will just make life a little easier. You have one, you don't have to put this VD on battery in your circuit. And then it's got a bunch of these circuit elements. And really, basically, it's the same approach you take over and over and over again in these problems with different degrees of difficulty. You you assume Vn is very negative, and you try to, for example, let's take this case, right? So this guy, I assume Vn is very negative first. I try to figure out, in that case, is the diode on or off? And if, so in this case, I looked at Vn being very negative. So out here, I decided that in that case, the diode is on, because if you look at this Vn, if it's very negative, it's pulling, and then by very negative means like minus infinity, minus 1,000,000 volts, just to conceptually ease in your mind having to worry about, resistor, exact resistor, or V sub B values. I'm not talking about like if Vn was minus 3 volts, I'd have to sit there and think. But if it's minus, 10,000 volts, this node is going to be less than this node, regardless, really, for VB of 2 volts or whatever. So kind of think in like extreme cases. So out here, is D1 on or off? And because this point here, the N part of the diode is less than the P part, we just say in the case of negative values, so out here and up to some breakpoint, the diode is on. So I basically redrew the circuit. So that circuit looks like looks like this. There's a diode and there is a battery. So you always want to redraw the circuit. So I redrew that as this with the diode being on. Now in the case of a ideal diode A, so this is the ideal diode, and on diode is just going to look like a shorted switch, and an off diode is going to look like an open switch. So I believe it's very important to actually to prevent yourself from getting confused, to redraw the circuit. So in this case, I redrew the circuit, okay, with just replacing the diode here, got replaced with a shorted switch. And so, okay, that sounds good. And then I looked at, okay, what happens if Vn now is very high, very positive, 10,000 volts, plus 10,000 volts, whatever. So in that case, we're forcing the N node to be higher than the P node, meaning that we're forcing that diode to be off. So again, I redrew that circuit and I just put in this off switch. It seems kind of like a stupid thing to do and an unnecessary extra step, but it really does. It's the recommended thing to do, and it does really help me to keep things straight. And as the circuits get more complicated, I think it's more and more necessary. So, and it kind of helps to calm the mind as well, let's say, during a test. Okay, and so basically what happens is, for example, in this case, if I redrew the circuit, so now we're looking at a negative value, you see that we shorted V sub B, got shorted to the output, and then it doesn't matter what Vn is, because V sub B, being a battery, it has very low output impedance, and as long as it's shorted to the output, it dictates what the output's going to be. So we're just going to get a flat, there's going to be no variation with Vn on V out. We're just going to have a flat 2 volts, because that's the value of V sub B given by the problem. And then at some point at V sub B, the diode turns off. So you move to this circuit. And basically you have Vn going through a resistor to V out. And in that case, V out is just going to follow V in with a slope of 1. Okay, so this ends up being your solution. Any question about that approach? Okay, so that's basically, I went. Go ahead.
Can I ask a question? Sorry about that. Can you scroll back up?
Sure.
All right. So right there. So just a quick question. I just want to see if I understood right. So when the diode is less than 2 volts, so that means it's like going on the negative side, quote unquote, if I can say that. That means that the diode is shorted, right? So VN really doesn't affect it because the battery's there because of VB, right?
Yep.
Oh, okay. So that's why it's flat 2 volts when the diode is on, right?
Right. Because VN is going through, VN is connected to that node through this resistor, which is, finite. It's some finite value. But this battery is a perfect device. So it has 0 output impedance. So it's going to win. If you're thinking in terms of a voltage divider or something like that, this guy is going to win every time over VN. But you had it right, exactly.
All right, thank you.
So the rest of these, very much the same way of looking at the problems. Each time I looked at, what I did was I looked at the circuit, went very negative, very positive, and decided if D1 was on or off, redrew the circuit, and then basically used that circuit to figure out what the equation was going to be. Okay, so that was problem 3.9. Okay, problem 3.10 was the same as 3.9, but instead of using the ideal voltage model, the problem asked for the constant voltage model. So again, the constant voltage model looks like VDID, and it's basically the diode turns on at some VD on voltage. And the problem didn't specifically say what that VD on should be. I will tell you guys on the quiz, but if you're not told, it's like 0.8 volts is a good, and that's what I picked. I think that's a good assumption. Okay, to use. So there, I did exactly the same approach, except, so this is what happens, is in this constant voltage model, if a diode is on, it also looks like a short, but it'll have a battery with the value of VD on in series. And if it's off, it still is like an open switch. It still has a battery, but the battery's not just sort of floating around there. But basically end up with, you have to replace the diode with that, which is, for example, I did here when the diode is on. And in this particular case, and then same with the VD off, I put it in here. And again, it doesn't really matter usually when the diode's off that you have that VD on battery. And so in this case, it had the effect, if you guys remember, it was flat in 3.9. It was flat at 2 volts. And then the breakpoint was like at 2 volts. So it was doing something like that. Then it brought this thing down in this particular case and in because of this diode model. But it could have done something else. But in this particular case, it basically shifted over the curve because of this VD on value. Okay, and then I did the same thing over and over and over again. I just sort of put in this VD on value whenever I wanted to replace the diode, redoing everything in 3.9. So 3.11, again, we have, like I mentioned, we have three curves, and it's asking for V out versus time now. So we're looking for this curve, okay? And so it's not V in minus V out anymore. So it's saying for the circuits in 3.9, I think it asked for the ideal diode just to keep, the ideal diode is obviously, it's like sort of simpler to deal with. So again, this is a nice warm up. So it asks to do this voltage versus time for the same set of problems. And the approach to take there, or the approach I took, was so superimpose the time graph on the V in versus V out graph. So this is this part. This part is the V in versus V out graph that we had in 3.9. And then I just said, okay, here I'm superimposing this time versus voltage. So this looks like, imagine if this is rotated by 90 degrees this way. It's basically voltage versus time. Whoops. Versus time. Oh. Okay, so like that with the input. So that's your input. And then the idea is if I have this as my input and try to visualize if this thing gets through this, so this is in, and it hits this curve, right? So whenever the curve is below, whenever the input is below this value, you end up with this V out value. Okay, and whenever V in is above this value, you end up getting this value. What you end up with is, this is the curve you end up with. So this is your input. I was gonna, whoops, we kind of like that. Okay, so that's the way to look at it. Here I did the same thing. So I said, okay, I'm gonna put time. I'm putting time here. And V in here, and then time and V out here. And here, when the input is doing this, this is this green is the curve we'll deal with. So when it's below, when the input's below 2 volts, it'll see this V in minus 2 volts. So it follows V in minus 2 volts. And whenever it dips up above this value, then it's going to hit 0. Okay. And so that's the V out versus T for that. Same thing here. Any questions about that?
No, Professor. I just would like to add like a friendly comment. Sometimes when you explain and you're pointing out something, I kind of get lost where you're pointing out. And there's on the options, on the tabs that you have the camera, then the text, and then you have something between the colors and the text option. If you click on it and use it to point out, that would be just my own thing. Sometimes I get like kind of lost where you're pointing out. If you don't mind using it just once in a while, I would greatly appreciate that. I was gonna tell you that like some lectures before, but I was kind of afraid, like, no, I didn't want to ask, but sometimes I get lost.
I appreciate it, Manuel. So this is the thing? Is this what you're looking for?
Yeah, Professor. Sometimes when you're pointing out and saying, oh, when you're saying something, referring to something specifically, I kind of get lost because I don't see any mark or anything in it.
Gotcha.
I'm trying to. Thank you, Professor.
Okay, sure thing. Thanks for pointing.
Thank you very much.
Thank you. I actually needed that too. Thank you.
Thanks.
Oh, feels good that I'm not the only one.
Yeah, me too.
Thanks, guys. Okay, so here we've got, so then move into problem 3.12. Um, I don't know. I guess it was just more difficult version of the same circuit, but it's really similar idea, V out minus V in, and ideal diode model. So, and I just a different set of circuits. So I did exactly the same thing. Nothing new here. Maybe it was just more difficult designs. Let's see. So that was, now again, do the same thing with constant voltage model. Any questions about these guys? Did you guys try to try these circuits? I hope you did. And then 3.14, the V versus time. God, same thing here. Same thing. Go to very negative VN, very positive VN, and look at the circuits. I think the main difference between these is that the diodes are like in parallel now with the resistor elements. So it adds a little bit of a, maybe makes the V out here equation a little bit more complicated. By the way, one of the things to think about is, okay, you have this slope here, right, and very negative and very positive. So here in this case, it goes to a constant voltage. And the question becomes, well, how do I know where the break point is? Okay, so I know that's my slope, but how do I know they meet here? They could easily meet somewhere. I guess in this case, it's not that complicated. But what I would do is I would make the two V outs the same. So I would do, R2 over R1 plus R2 V in, which is this guy here, equal to this guy. So they should basically run into the same point. At this point, they will be, those two curves better be equal, and then get a value for Vn, where is this happening? And from this kind of circuit, you can get Vn. Now, of course, you have to make assumptions. R1 and R2 haven't been given as part of this problem. I just kind of assumed they were the same value, just to always make this, a half. If R1 is equal to R2. It wasn't really given. I think it changes the breakpoint, which wasn't specifically asked for, but just something to help find the breakpoint.
Professor?
Yeah.
Is like pretty much doing that between the two states of the diode being on and off, just like ensuring that like the graph is continuous and that like they meet at that one point of where the diodes changes states.
Yeah, and also, that's certainly a big part of it. But also, sometimes it was hard for me to say, okay, well, this is like the question was where, like, for example, in this circuit, right? You had something, we had this part of the circuit which was very negative, and this part of the circuit which was very positive. I mean, it could just as easily, the breakpoint, in my mind anyway, could have been over here between a slope of 1 and this slope. So the question is, well, why should it be here versus here? So you have to find a way, if you actually had values for R1 and R2, you have to find a way to find out where this breakpoint is to get a good idea for where the curve would meet. And again, it didn't specifically ask for it, but it helped me kind of try to visualize the graph. Did that help, Adrian?
Mhm. Yeah, thank you.
Um,
Professor, can you explain, sorry, why it's a slope of 1 when the diode is on?
and the diode is on. Sure. So what happens is, look at, so when the diode is on, we have this circuit, right? So when you have uh, this battery here, this is the VD on of the diode in parallel with the resistor. It basically it goes around the resistor. So it's like basically you're putting in a voltage of Vn plus Vn minus Vd on over in this node. Okay, because you're just the signal is going straight through this battery, so the signal is going this way and establishing Vn minus Vd on this node. So basically the equation ends up being V out is Vn minus Vd on. So if you look at the slope, we're drawing the slope between V out and Vn. And the multiplier here is basically 1. So there, this gives you a slope of 1. So it's this multiplier 1 plus this offset VD on. Does that make sense?
Oh, I see. So the offset of VD on is kind of like where you would draw the breakpoint, right?
Yeah, it's where
okay.
It's where you would be. Yes, yes. But you need, the problem is you don't know. It's where you would draw the breakpoint, but not quite. It's where Vn makes the diode switch from on to off. So if you want to really know the breakpoint, what you'd have to do is take this thing and say R2 over R1 plus R2 Vn is equal to this guy. And then figure out Vn. Whatever that is, it's going to be I'm bringing Vn to the other side. I shouldn't have done that. Sorry. No, let me do it the other way. Let me bring this guy to this side. So no VD on. So Vn minus Vn R2 over R1 plus R2 is equal to VD on. So I'm going to take Vn out, 1 minus R2 over R1 plus R2 is equal to VD on. So, and then let's see, this guy turns into, I'm running out of space here, but Vn R1, let me do it over here. Vn R1 plus R2 minus R2 over R1 plus R2 is equal to VD on. And these two things get canceled. So when Vn is R1 plus R2 over R1 VD on. So you need specific values for these things. That's the breakpoint. That'll tell you where this breaks. So it's kind of
Professor.
Yeah, go ahead.
Sorry to interrupt. I'll do it after you finish.
Okay, so basically, the exact value of R1, R2, or when it tells you Vn is going to be here versus here. This VD on is part of that equation, but it doesn't exactly break at, there's no guarantee that the break is going to be right at VD on one way or another, but it's going to be where this happens. Go ahead.
So, Professor, just a quick question. So, if I had to say the point in coordinates like x, comma y, we'll have as x all that expression you just derived, correct? Comma be the on, correct?
Yep.
Thank you.
Any other questions about that, guys?
So, Professor, just a small question. So, is this how we're able to manipulate circuits with diodes to be on at a specific voltage? So, let's say I was trying to create some circuit and I was saying, hey, I wanted to turn on at this voltage. This is kind of how you would figure it out.
Exactly, exactly. So you would basically start playing around with values of R1, R2 in different configuration. Let's say you wanted to have a circuit for whatever reason that had two different slopes, but a different breakpoint, then you could adjust R1 and R2 to move this breakpoint around. And this is part of the reason why it's important to be able to do a hand analysis, because if you're using SPICE, if I give you guys specifically R1, R2 values in SPICE, you'll get a certain curve, but you won't have an insight into how you can move that curve around with different, say, like, you can adjust this. In this particular case, you can adjust this slope here, and you can't adjust this slope. The slope is always going to be 1, but you can adjust this slope and you can adjust the breakpoints, and you won't really get that insight if you just are running simulations. But yeah, in fact, that's exactly how you basically use different topologies, different types of circuits, and adjust values. So you can get like much different curves here. You can adjust. Oops, sorry. Let's see, where is a good example? I guess I'd have to look at an example of when you can adjust both slopes. But you can certainly have a case where you go to a sort of a limiting circuit versus a different slope, etc. Okay. Okay. So, any other questions, guys? If not, I'll move to 3.24, which is now the third types of graph. It's talking about current as a function of Vn. So we need to draw, so we have Vn, whereas there's current, and it wants the current through the diode. So for example, it wants the current through this D1 and the current through this R1 circuit. So it wants currents through both of these guys as we sweep Vn. So what I did, these are, were these new problems? I think these were new. Yeah, these were sort of new circuits. And what I did was I basically just did a similar thing where I looked at Vn being very negative, Vn being very positive for each one. But this time I looked at the currents as opposed to the voltages, what the currents would look like. So this red is the current through the resistor R1, and the green is the current through the diode D1. Went through the same things, except when I did the equation, I looked at the currents. See anything tricky? I guess I don't think there's anything tricky here. It was just doing the currents. Here, V in versus V out. Yeah, I don't think there was anything particularly tricky about that. It was just things were getting a little bit more complicated. I think this is an example of how I tried to show you guys how to calculate the breakpoint specifically. Same here, trying to figure out the breakpoints. It helped me to visualize at least. Again, same thing with the currents. I don't know if I have anything to say specifically. Again, the green is the diode current as a function of Vn. So I versus Vn, diode current, and I have the resistor current in red. Any questions about any of those? I didn't, it just seemed like different circuits. I don't like, it just was like trying different circuits. I don't know. Nothing noticeably different to me. Okay, now things started getting more complicated at 3.27. So what happened in 3.27 is you have two diodes now. You have D1 and D2. So what does that mean? So when we had only one diode, there was only one breakpoint in our circuit. It was either D1 could be on or D1 could be off. Now, what can happen is you can have, you have two diodes, so you could have potentially four combinations, or like a binary kind of thing. Both diodes could be off. The first one could be on, the second one could be off, or the second one could be off, the first one could be on, or they could both be on. So now you have to look at, cases. I still start with the case when Vn is very negative. Okay, in this case, I did this. And in that case, for example, this node here goes very, very negative. So the P of this diode is very low. So I'm guaranteeing this diode is going to be off. And also through this resistor, the P of this diode is also very low. So basically both diodes are off. And was this as a constant voltage model. So both of these guys were off. And then, I came up with this circuit and looked V out was just going to be equal to Vn because it's going through this resistor. Then I looked at the very positive case, okay, out here. If Vn is very positive, it guarantees to turn on D1. And through this resistor, if Vn is very, very positive, it's guaranteeing to turn on D2. So in this case, both D1 and D2 are on. Okay, and I redrew the circuit and got this V out versus Vn in each case. Okay, and then there was this case where we got to figure out what's happening in the middle. And so at some point, D1 goes off and D2 goes on. And I came up with the equation for that. And then I went through the same path of trying to figure out the breakpoints between, because we have two breakpoints now. We have one from this region here to this region, and then one from this region to this region. And so I had to equate these two equations and then these two equations to come up with the breakpoints. So all of a sudden, things got a lot more complicated with two diodes.
Professor, quick question. How could you tell that one is going to be off and the other one is going to be on? How could you kind of like insightfully see it, or how is so?
I think what I decided was because of this battery here, VB, as VN goes higher and higher, I decided at some point this guy was gonna sort of would would essentially still be off, and that this guy, because there's no battery on this panel,
Oh,
you see this,
okay. Oh, I see it. I see it now.
I decided that one's gonna turn on sooner. But
Even though we don't know what the VB value is, right?
actually the VB, yeah, what was VB? I think the VB is given. I think the VB was given as 2 volts, I believe.
Okay, does make sense now. Thank you.
Professor?
Yeah.
So you were saying it's going to be like binary where they're both off, they're both on, or one or the other is on? So do we...
Could be.
Oh, it could be. So it doesn't have to be 4 cases every time?
It doesn't have to be 4 cases every time. So in this case, it was only sort of 3 cases.
Okay.
How did I know that? Good question. I don't have a good answer for you guys. I guess,
Professor,
yeah.
maybe if we say that VB is equals to 2, and then when VN is equals to 1, the potential difference, even though it's greater than 0.8, and the diode should be on, still the potential difference is negative from the positive side or the anode side, right? That's the way I see it, and kind of makes sense.
Okay, that makes sense.
Yeah, I saw that just VB makes it so that diode 1, there's no other case where diode 1 would be on and diode 2 would be off. If it's VB, that makes it.
Yeah.
It does make sense the way you explained it at the beginning.
Yeah, but I think it's you have to consider it, let's say. And then maybe the case that there isn't any, but you'd still have to consider it. Like in this case, again, it was because why in this case? I think in this case I just decided just because they were they were going, diode 1 is pointing in that direction, diode 2 is pointing that direction in the same node, although the other side is connected to different things. I just said I don't think there's a way for them both to be on. So I didn't really have much of a better reason for that. Let's see, same in this case. Let's see, why did I think in this case, I decided that because, again, for diode D1 to turn on at any point, you'd have to have a high enough voltage that, basically you'd get 2 diode drops through here versus here. And I thought there wouldn't be a case where you'd have high enough voltage building up here to give you a VD on through here. So I don't know if I had like really good cases. You could basically, I think you could consider all 4, sorry. Maybe the wise choice. I'm trying to think, is there a better way to explain this as opposed to just getting a feel for it? I think you could just look at all 4 but I think by inspection you could just try to guess at whether it's going to be 4 or 3. Seems like every single one of them was 3 breakpoints. Anyway, so then 3.28 was, I think it was the same circuits, but you're basically looking at current through R1 and D1, and as opposed to the V again. So this is again V versus I. So same thing, except I'm calculating. First, I'm calculating the voltages, and for there, I'm just coming up with the currents. And I'm kind of just, again, because these break, it hasn't specifically asked for the breakpoints, but qualitatively for the breakpoints, I was just sort of coming up with these relationships. So like this is a full equation for ID1, but when you look at the slope of its relationship with Vn, you just end up with Vn over R2, and the rest of everything is, offsets. But, at this point, I think you guys are saying things are getting pretty complicated, right? I feel like these were pretty involved problems to analyze. But going back to what I was saying is, imagine if you had this circuit and you were doing, using SPICE to simulate this circuit. It'd be fine as long as I gave you R1 and R2 values. But if you don't have a way to do analysis to see how these curves would look with respect to R1 and R2, don't have equations, then you could sit around and start adjusting R1 and R2 and VB and stuff like that, basically for hours and hours and hours of rerunning simulations to get what you want, because you don't know how these things are affecting these curves if you don't have these, these behavior equations, etc. So, and actually I see that at work whenever we get, we don't do a lot of diode circuits, but we do a lot of transistor circuits. And a lot of times, new engineers, younger engineers, they have a tendency to sort of keep running simulations over and over again and never doing kind of a hand analysis or get a feel for what the circuit's doing. So that's where this sort of shows the value of these hand analysis. Okay, so same stuff. Nothing. Boy, these things we're getting, these were pretty complicated. What was this? Same stuff, I guess. Just various levels of complications. Unless you guys have questions about any of these things, but using the same techniques. Anything remarkable? Again, current versus voltage. Okay, so coming down the home stretch here, so 3.31, what was it asking? I think it was asking for us to find the change in output voltage if there was a small change in input voltage. And with some assumption of VD on as around 800 millivolts. And really, I think what can I say about this? I think the main thing was trying to decide if there was enough, so look at this case where So if you want to decide a VN, if diode 1 and diode 2, or really what you're trying to decide is if they're both on, and that, what happens in the case when VN goes up. In this case, it was at 2.4 volts, right? And then trying to figure out if that gives you enough sort of headroom to be able to turn on both diodes. Because if both diodes are on, basically you have a situation where VN, basically V out is kind of VN minus a diode drop because it's just sitting on the other side. But that's assuming that the diode is on. So it's kind of stuff like that, I guess, is just trying to decide, are the diodes on, and then what kind of voltage drop you might get from V in to V out. In this case, V out would end up being, as soon as you turned on D2, that was going to hold V out at a constant voltage. So V out wasn't going to shift. So in both cases, as V in is changing from 2.4 volts, 2.5 volts, it didn't matter. In both cases, the diode was on here and was holding the output at the same voltage. And I think it was similar kind of thinking here. This was similar, except the input was a current, which I found a little bit confusing, or maybe it was just late at night or something. But it ended up basically what did I do? I ended up in some of them needing to use the small signal approximation to get the output. Most of them, I think. This seemed like 3.33 seemed like a really simple problem. I don't know. Well, all the answers were the same, but I just remember it being sort of simple. Any questions about that set of problems? They're all kind of along the same lines. I guess they were trying to get to the small signal, give you some examples of small signal analysis.
Professor, can I ask you a question?
Sure.
Could we try out rigorously just one example of the small signal, just so we could get an example?
Sure. Let's see, what's a good one? I think let's look at this one here.
Thank you.
B, sure. So basically in B, we have I in is changing from 3 milliamps to 3.1 milliamps. Okay. So if you remember, in small signal, sort of a small signal analysis, the first step was to figure out the bias point. So in this case, the bias point is 3 milliamps, and the small signal value is 0.1 milliamps. So notice the input is only shifting over by 0.1 milliamps. So first thing we do is we figure out at this bias point, what does the small signal circuit look like? And remember that the small signal approximation of a diode was a resistor. Again, this is assuming a very small voltage, so this 100 microamps or 0.1 milliamps. So it was a diode where RD was VT over I sub whatever is the I bias, say. So and then VT is this 26 millivolts, we assumed room temperature, and I was 3 milliamps, again, this bias point. So this gives us this small signal resistance of 8.67 ohms. So if I was going to redraw this, this circuit, let's Sorry guys, I'm trying to figure out a way to, so as I can redraw this as IN. This is the small signal. So just for the, instead of saying IN, I should give it small IN, which is 0.1 milliamp. So this diode would look like a resistor. Then I have another, the resistor R1 is just a resistor, doesn't matter. And this diode D2, so this is D1. And D2 is gonna look like another resistor with value R sub D. So both of these, because the current is the same to both of them, they're both gonna be 8.67 ohms. 8.67 ohms. And then the only thing you have here, because this is V out, is you basically are looking at, what is the current going to do as that current goes through these resistors. Basically, you got to think about this current running through this, which is 1K ohm plus 8.67. So you got that current, 0.1 milliamp running through these two. And it gives you a change in voltage of 0.1009 volts.
Thank you, Professor. That really helped a lot. Thank you.
Sure. Yeah, it was basically, if you guys remember, there was a 3-step procedure for doing small signal analysis. The first step was to figure out the bias point, which in this case was the 3 milliamps. The second step was to figure out the equivalent resistance values for the diodes. And the third step is, redraw the schematic with those resistor values and do the analysis. So it's sort of a 3-step procedure.
Professor,
yeah.
Quick question. What if we had like a parallel circuitry? We have to use division current rule? Or how would it be?
Yeah. I mean, depends on the specifics of the circuit. But if you'd be in deep, like things would get really complicated if you had 2 diodes in parallel. Okay.
Okay.
Because then you'd have to make a lot of assumptions about how much current goes through each one. But if you had 2 resistors in parallel, things would be a lot easier. But if you had 2 diodes in parallel, you would have to assume it's ideal, or ideal diodes, which I guess you could. Yeah, and then you'd have to say the current goes through, half the current goes through one versus the other. So for example, if you had, now I'm talking off the cuff here, so hopefully I don't get this wrong, but if you had, for the sake of discussion, a circuit where you had 2 diodes with a certain bias current, I don't know, like there was a certain bias current, 3 milliamps, then I guess I would assume these are ideal, and I would sort of have 1.5 milliamp bias current through that one and 1.5 milliamp bias current through that one.
So now the bias current, it'll be 0.5 milliamps instead of 1 milliamp?
Well, assuming you had 3 milliamps, you would be 1.5 milliamps in this case and 1.5 milliamp. Oh, the input you're talking about?
Yeah. The one that increases by how much was it?
Yeah.
1 milliamp, right?
1.
So
yeah.
you're also cutting it in half as well, or?
At that point, so let's take a look here. So again, I'm talking off the cuff, so hopefully I'm not gonna steer you guys wrong. So let's say we do that and we come out here, and then you come up with R sub D values for at I being 1.5 milliamp. Okay, so that's gonna make your R sub D twice as big. So let's say 17 ohms. Okay, so you're gonna have R sub D here and R sub D here. This is going to be 17 ohms. This is going to be 17 ohms. But, you know, I think the simple thing you could do there is this is two resistors in parallel. So you have an equation of what is the equivalent resistance for two resistors in parallel, right? So you calculate that and you calculate that current 0.1 milliamp going through that effective parallel resistors. Do you know what I'm saying?
Yeah.
So here,
I think so.
this, the equivalent of this is, so 1 over sort of R effective is, what is it, 1 over R sub D plus 1 over R sub D. So you can figure out a effective resistance.
Okay.
Does that make sense?
Yeah.
It basically has ended up being 8.67. It's like, it looked like this guy is 8.67 ohms, I believe. Hope I'm not wrong about that. Does that make sense, Manuel? So what you do is you figure out the bias current, and then you redraw the schematic. And then we're in a schematic, if you have two resistors in parallel, usually the wise choice is, if you have two resistors in parallel, you kind of replace them with one resistor with the equation of two resistors in parallel, which is sort of just simple circuit analysis, and then do your calculations based on that.
Okay. Thank you.
Yeah. Okay.
That explains a lot.
Okay. Sure. Okay, so 3.34, guys, this is now, we're talking about half-wave rectifiers, and man, these can get tricky. So basically, you know, it gives you input sine wave with a peak value VP, and this is a very important thing, this initial condition. Okay, so this is where I personally get it wrong a lot of times, and I've seen students get it wrong on, you know, solving problems, etc. Is make sure you're coming up with the right start point for this, because that tells you, as your sine wave's picking up, it tells you if this is 0.5 volts. And again, I assume that certain value of, I think the problem said assume 5 volts V sub P, but it tells you that you're going to have something like this, and then it's going to turn on after a while. Okay, so if, for example, let's say if this initial condition was like 10 volts, your answer would be completely, sorry guys, your answer would be completely different. Did I stop sharing my screen?
Yeah.
Yeah.
You actually did.
Just give me one second. Okay, so again, if you really keep an eye on this initial condition, which is what happens at initial condition is what happens at time 0. Okay, so Vn, you've got a sine wave. So you know what it's going to do. It's going to start at 0. It's going to go up to V sub P at some point. And then the initial condition is 0.5 volts. So you know it's going to be sitting there, and at some point it's going to turn on when this input value goes to this 0.5 volt plus a VD on. It's going to turn on and then start following this till it gets to this peak, and it starts coming down, and then the diode turns off, and it'll keep that value. And this problem, the diode was just facing the other direction. So in that way, the diode, as long as this point is higher than this point, the diode is off. So the capacitor keeps its 0.5 volts value, okay, until this point gets more negative than VD on minus this 0.5. And then at this point, this input is more negative. Then the diode turns on, starts following this guy, and then the diode turns off when this thing has this high going curve again. And then we had 3.36 and 3.37, which was the half wave rectifier. I was asking for the ripple voltage. And in this case, it had given the other values. It had the ripple voltage, and I wanted to know the smoothing capacitor. But again, I feel like the half wave rectifier and the full wave rectifier questions that you guys get, although I guess if you thinking about deriving the equation, it could be complicated, but the actual problems are actually pretty simple. You just have one equation to get, sort of, or maybe two equations here. Okay, full wave rectifier. So those were the other questions. It was like sort of a similar thing. Again, simple equations. It's kind of a complicated concept, but it's a simple equation. So if you guys, my advice to you guys is just in case there's some like rectifier questions in the class, maybe consider, when you're doing the homeworks, start both at the end and at the beginning. So do the rectifier, make sure you do the rectifier questions, because I feel like they're fairly simple. And, if a rectifier question comes up, you'll be able to solve it in the quiz. Whereas if you're serially starting the homework from the beginning to the end, I don't know your schedules, etc., you might run out of time and never look at the rectifier questions because you're still, solving one of these voltage in versus voltage out problems. But if you hit the rectifier, so you never get to the rectifier, although the rectifier questions I feel are pretty simple and they don't necessarily have, you don't really need to know the stuff from the beginning problems of the homework to be able to solve these. Okay, guys, we're at 6:43, so I'm going to stop here. Any other questions? Any specific questions?
Yeah, I got a specific question, but I want to wait until the end, Professor, if you don't mind.
Okay, I'm done. So just one thing again. So guys, remember the quiz is next Tuesday, the 13th. Before then, I'm gonna send you guys your quiz 1 values. Sorry, I'm kind of falling behind. I haven't sent, I think you guys have your scores, but I haven't sent you back your quizzes with suggestions, which I'll have for each one of you guys, just for advice about how to do well in the future quizzes. I think the main thing I saw that like easy, let's say easy points lost, which is what you guys should ward off against, is don't screw up your math. Okay, like sometimes it was a kilo ohm resistance values, and instead of a kilo ohm, you'd put in, instead of 1 times 10 to the third, you just put in 1 in your calculation, and that just sort of sent the result to some really sort of crazy number, and it got you all confused. So be careful don't, at least be careful, stay calm, and don't make calculation mistakes sort of calmly write down your equations and make sure you have, if it's in this case, like, I don't know, I'm just picking as random, 1,000 microfarads, don't put in 1,000 farads. Make sure it's microfarads. Otherwise, you would end up with some crazy number here. And in this case, like, I'm going to be pretty nice about scoring. Like, if it's something simple like this, but like if this value from this calculation feeds into another step in the problem, and you're already in some crazy number here, you won't even know what to do in the second half, and there you definitely lose a lot of points. So just my suggestion is be careful with your calculations. Okay, Manuel, go ahead.
Oh no, Professor, I already found my answer.
Okay.
Sorry about that. Yeah.
Okay. No problem, guys. So, and then,
Sir.
Yeah.
Sorry to interrupt. You can go ahead. I'll ask after. Oh, so just had a question. The quiz 1, I wasn't able to submit it to Grayscope, but I emailed it to you, so not sure where to check for that.
Did you get assigned a grade from Blackboard?
Not sure. Not sure where I should check. Honestly, let me check.
Okay. I'll look for it. Especially, can you send me an email? Just remind me.
Oh wait, never mind, Professor. My bad. False alarm. I see it now. I see it. I wasn't looking. Thank you.
Okay, sure. Okay.
Well, thank you, Professor.
Okay, thanks, guys. Good luck. And on Thursday, I'll start on bipolar transistors, which on Thursday's material will not be covered in quiz 2. So, all right, guys.
Thank you so much, Professor. Have a good one.
Thank you, Professor.
Thanks.
Professor, have a good one.
Thanks. Bye.
Thank you, Professor.